Hi, my name is Jasminder here. I'm a solution architect here at Amazon Web Services, supporting customers within the aerospace and satellite industry. I'm so glad to have you joining us today for this session about Eyes on Earth. Eyes on Earth refers to the capability of Earth observation through satellites and space-based sensors. Today, we're going to talk about what's happening in Earth observation at present. Satellites, the orbits of satellites, which is where they operate, and the more active use cases we see in the industry. From there, we'll move on to how to architect for Earth observation on AWS. I'll walk you through a typical architecture for an application, which takes data from satellites and makes it available to customers anywhere on the planet. My colleague Seema will walk us through the role of machine learning within Earth observation and how it can deliver insights to customers. Overall, our aim for this session is to inform you about what is available to all the builders out there and how you can start experimenting and building with it. Let's dive in. We're all entering a new space age, which is very exciting. Space in the past used to be about astronomy, the observation of the stars and galaxies, observing the building blocks of the universe. From there, we observed a space race between nations, the first into space, into orbit, the first to reach our moon and land on it, an age of many firsts. We've come a long way from then to see cooperation in space between multiple countries, to build international space stations manned by people from all over the world. In the next step of our journey, we see space opening up where commercial companies are playing a far greater role in innovation and bringing new solutions to market, all the way from launching satellites and people to observing planet Earth in new ways every single day. Today, we're seeing more and more collaboration between government agencies and private enterprises towards achieving goals like robots in space, on the moon, and on Mars. The space industry is growing rapidly globally. My customers always tell me that their solutions are global solutions. They may have been built in one part of the world, but because of the nature of the space industry, the solutions are applicable everywhere. We're observing more and more humans flying into space, and we're all looking forward to programs like NASA's Artemis mission, which aims to send astronauts back to the moon by 2024. According to the UN, since inception in 1958, there have been more than 12,000 satellites in space. In 2020 alone, more than 1,200 satellites were launched into orbit. That was a record as the highest number of satellites launched in a year. But then, in 2021, more than 1,800 satellites were launched. We beat our previous record. This represented a 41% growth in assets launched into space. I'm sure you've all guessed the overall theme here. There are more and more satellites going into orbit every year. One natural question that is asked is, why so many satellites? And what purpose are they fulfilling? The bulk of the contribution comes from communication. Think about mobile communication, satellite TV, and internet access. Internet access requirements are also being met through the use of satellite constellations, which we will talk about in a little bit. The second largest contributor at present are Earth observation satellites. It is almost 30% of current scope. Earth observation is the ability to look at our planet every day, taking many images and then processing them into usable data, like what's the weather going to be tomorrow? What is the impact to my crops? And what is the state of our assets? Now, I know when we talk about Earth observation, the first use case everybody thinks about is weather prediction. However, Earth observation data is making a big difference in so many other domains, like predicting extreme weather events, where being able to detect early can result in lives being saved. Detection of oil spills is also very important, because when it happens, we want to know about it as soon as possible, so we can take steps to reduce its impact. Earth observation data and insights are making a significant impact to the agricultural community by informing the farmer on how his crops and land are performing, how much water is required to feed the crops without waste. The insurance industry is also using satellite imagery to better understand the impact of a natural disaster, like an earthquake or floods, and speed up the claims processing. And one last use case, which is near and dear to me, is the ability to detect disasters like bushfires. I reflect back on the bushfires in Australia in 2020 and acknowledge that being able to detect bushfires within minutes can and has resulted in lives being saved. As we discuss these use cases and Earth observation, I believe it is important to understand a little bit more about satellites and their orbits. You can think of orbits as highways around our planet where satellites are traveling. The first one is low Earth orbit, or LEO. In low Earth orbit, satellites are at an altitude between 160 kilometers and 2,000 kilometers. For good reference, airplanes fly between 11 and 14 kilometers. Even when, with the low Earth orbit, which is the closest to us, satellites are still very high. Satellites in low Earth orbit can complete a full round trip around the planet in about 2 hours, which I'm sure you'll agree is very fast. If you're curious, they're traveling at around 15,000 kilometers per hour, and they do around 11 orbits every day. Because of these reasons, they're great for weather forecasting, imaging Earth, and communications. We could say that one disadvantage of being so close to Earth is that they can only observe a small part of the planet because they're very close. However, this can also be an advantage because it allows for imaging to occur at very high resolutions, which can tell us a lot of detail about an area. Now, if you want to observe a particular area all the time for, let's say, bushfires or forest fires, and we have a single satellite, which will take a few hours to come back around, it does not make for a great solution. That's why a single satellite in low Earth orbit cannot solve what we call the persistent observation problem. Let's keep this challenge in mind as we progress here, because we will see how it is being addressed at the moment. Another orbit that is relevant to this conversation is geosynchronous orbit. Within this orbit, satellites are located at a very particular position above the equator, and they stay at an altitude of around 35,000 kilometers. Because of that very particular position, satellites in geosynchronous orbit continue to rotate with the planet, which means that the satellite is always on top of the same region. As you can imagine, this is great for communications and observing weather changes for a particular part of the world. As they're so far away, though, we would only need 3 geosynchronous satellites to cover the entire planet. We can use fixed antennas because the satellites don't move, and we don't need to track them because they're not moving around the planet, they're moving with it. One disadvantage here is that they are more expensive to maintain, and because they're so far away, the resolution of the images is not as good as satellites in low Earth orbit. If you come back to our persistent observation problem, then you'll say that these satellites may be great because they're always on top of the same region. But their image resolution is not so great because they're so far away. So maybe they are still not the solution to our problem. Some companies have tried to solve this problem using planes. You can have a plane flying above an area, but this can be challenging because the plane needs a pilot, and the pilot will need to rest, and we also need to refuel the plane. Another solution is to use drones, but drones are also highly regulated in many countries. So again, not a great solution to our problem. I wonder what could be the solution to this problem. One solution is satellite constellations, which is one of my favorite topics. Constellations is a set of satellites which work together as a system. A constellation can be made up of tens of satellites or hundreds or even thousands of satellites all working together to cover the whole planet. Satellite constellations are viable thanks to the development of something called autonomous flying. Flying in space can be challenging as the journey may not be very smooth all the time. From time to time, it may be important to realign the satellite. Autonomous flying allows the satellites to have a sense of self-awareness. They're aware of their position and the position of other satellites as well. Another important contributor for constellations is the development of microsatellites. The satellites weigh less than 100 kilograms, and we even have nanosatellites that weigh less than 10 kilograms. As you can see, the persistent observation problem is solved using satellite constellations in low Earth orbit. In this way, you have persistent coverage and still great image resolution. Let's observe what a typical AWS architecture looks like, which enables you to downlink your satellite imagery on demand. Let's assume you have a satellite. Now you'll need a ground station capability to downlink data such as satellite imagery from your satellite. AWS Ground Station is a fully managed service that lets you control satellite communications, process data, and scale your operations without having to worry about building or managing your own ground station infrastructure. Using AWS Ground Station, you can schedule contacts with your satellite and downlink data to any AWS region in the world, which means you could downlink your data using the ground station in Sydney and have your data delivered to the AWS region in Singapore. You could even schedule multiple passes over multiple ground stations and download data multiple times a day. Your data gets stored in Amazon S3 bucket of your choice. Raw satellite imagery requires processing in order to make it readable. Here, you have a few choices available to you. You can use Lambda, which is a compute service that lets you run code without provisioning or managing servers. With Lambda, you can run code for virtually any type of application or backend service. All you need to do is supply your code in one of the languages that Lambda supports. Or you could use AWS Fargate, which is a serverless, pay-as-you-go compute engine that lets you focus on building applications without managing servers. Or you can use AWS Batch, which is a set of batch management capabilities that enables developers, scientists, and engineers to easily and efficiently run hundreds of thousands of batch computing jobs on AWS. Processed imagery can be further stored in different Amazon S3 buckets, and all the metadata can be stored in Amazon DynamoDB, which is a fully managed NoSQL database service that provides fast and predictable performance with seamless capacity. You can choose to archive older satellite imagery automatically in Amazon Glacier or Glacier Deep Archive for long-term storage, or make it available to your customers directly from S3. But when you have satellites in low Earth orbit performing multiple passes a day, the amount of data you will generate can be in the tens of gigabytes or even more. So the question arises, how best can we analyze this data to draw out insights from it? Here's my colleague Seema Gupta, who will talk about how we can leverage machine learning on AWS to address these challenges. Seema, over to you.
Thank you, Jasminder, and thank you to our audience. Let's start with some of the challenges that we might face with satellite imagery. To begin with, satellite imagery of sufficient resolution and cadence is expensive. Adding to that, while deriving decisions from satellite imagery, time is key. For example, in case of wildfires, it might just take one bucket of water to address a small fire versus a lot of community efforts and resources if we delay by a few minutes and fire spreads. Some of the other challenges are about data sets. Images from satellite imagery would have large images with thousands and thousands of pixels. Getting a subset of pixels to identify a particular object is time consuming. The data sets itself are large, so downloading and keeping it before starting the model training could be expensive. Last, there is no standardization of formats, which could mean lots of pre-processing. At times, we also get data sets in form of increments. Going a bit technical, ML use cases for satellite imagery could mean different things. The first one is object detection. In object detection, we might want to detect objects like ships, aircrafts, boats, etc. Another application could be land cover classification, where companies might be trying to label each pixel in the imagery as belonging to a particular class. As an example, the pixels can belong to vegetation, deforested areas, water bodies, and so on. Another common application is change detection. In change detection, users might want to look at satellite imagery to understand where within areas of interest changes are happening, what kind of change is happening, and when did it start or when did it end. Before we move forward, let me share that based on our experience, we understand that data acquisition can be time-consuming and expensive process, and AWS can help. The AWS Open Data Sponsorship Program makes high-value, cloud-optimized data sets publicly available on AWS. We work with data providers to democratize access to data by making it available to the public for analysis on AWS. The registry of open data on AWS helps you discover and share data sets that are available via AWS resources. You can find data sets from many different domains, including geospatial, through this. Here is a screenshot of some of the geospatial data sets available on AWS. Some of our customers are creating very innovative solutions using these data sets at optimized cost. One of such customers is the Blue Dot Water Observatory, which is an Earth observation-based solution that provides reliable and timely information about surface water levels across the globe. It uses Sentinel-2 satellite data on AWS to monitor water bodies around the world. What is interesting here is that working with AWS Open Data made the solution very cost-effective. Now, there are multiple ways to run machine learning on AWS. Customers who are very familiar with containers and open source tools like Kubernetes can continue to run their machine learning workloads on Kubernetes using AWS. One of AWS customers, XA, analyzes image data from third-party ground-based camera and satellite sources to accurately detect and predict wildfires. They have leveraged Amazon Elastic Kubernetes service to run their machine learning and have built an efficient wildfire detection platform to inform relevant authorities of potential wildfires within 3 minutes of smoke detection. Capella Space, a provider of on-demand Earth observation data by synthetic aperture radar or SAR, is leveraging Amazon Sagemaker, AWS's ML platform, to build complex ML models on SAR satellite imagery. By applying ML to SAR imagery, Capella can begin automatically detect global events in near real time without being hindered by weather or time of the day. Talking about ML on AWS, at AWS, we look at machine learning as a 3-layered stack. In the bottom layer, we have deep learning frameworks and optimized infrastructure like GPUs and CPUs for machine learning workloads. In the middle layer is our machine learning platform called Sagemaker, which is a studio-based machine learning platform. In the top layer, we have pre-trained AI services which provide ready-made intelligence for your applications and workflows without needing any machine learning experience. AI services address some of the common use cases such as personalized recommendations, modernization of your contact center, improving safety and security, and increasing customer engagement. In the next few minutes, we will dive deep into Amazon SageMaker features which could help geospatial use cases. The machine learning workflow is iterative and complex. SageMaker offers features in every phase of ML lifecycle. In the first phase of collecting and preparing data with geospatial use cases, one of the challenges is that there are limited amounts of open source data sets out there. These are great for doing some initial prototyping work, but when customers want to take these models into production and do unique analytics on that data, they might build data sets, sometimes even from scratch. Amazon SageMaker Ground Truth, a feature within Amazon SageMaker, has a built-in labeling capability, which makes it very easy for you to be able to label vast amount of data. Ground Truth also makes it very easy to access labelers through Amazon Mechanical Turk, Amazon approved vendors, or using private human labelers. Ground Truth provides built-in data labeling workflows which support 3D point clouds, videos, images, and text. When Capella team couldn't provide the entire image into a data labeling workflow, as the images are very high resolution, they solved this issue by building a pre-tiling workflow to break the large image into smaller tiles. Then they applied some basic filtering to apply image classification algorithm to filter tiles that might have sea cover or they were covered by clouds and obscured, so they couldn't actually label anything in those tiles anyways. This way, the workers had to look at a lot less tiles, making pre-processing easy for them. Moving to next step. To decide which algorithm to choose, you can choose built-in algorithms for things like segmentation and object detection to do basic training and learn about your data. And you can also use custom algorithms for advanced training. With Sagemaker, you can easily train and tune ML models using built-in tools to manage and track training experiments and automatically choose optimal hyperparameters. Sagemaker can automatically scale infrastructure up or down based on your training job requirements. With Sagemaker, you can add either data parallelism or model parallelism to your training script with a few lines of code. Sagemaker helps you decoupling your development environment from your model training environment so that you can use higher configuration only for your model training. Sagemaker provides capability to stream data to training clusters, which could be very useful as high-resolution image datasets can be quite large. There is also a capability to checkpoint your models. With this, you can start your training with a subset of labeled data and add more, and when ready, without having to start from scratch. Another useful feature of Sagemaker is to be able to train machine learning models using managed Amazon EC2 Spot instances instead of on-demand instances. Sagemaker manages the Spot interruptions on your behalf. With high-resolution geospatial images, inference can be quite expensive. Amazon Sagemaker offers more than 70 instant types with varying levels of compute and memory, including Amazon EC2 Inf1 instances based on AWS Inferentia, high-performance ML inference chips designed and built by AWS and GPU instances. The model could be deployed with just one API call. For use cases with intermittent and unpredictable usage pattern, which could be the case with geospatial use cases, Amazon Sagemaker serverless inference, currently in preview, allows you to deploy ML models on pay-per-use pricing. This means you pay only for the compute capacity used to run the inference request and not for periods of no traffic. Here is a reference architecture of how you can use Amazon Sagemaker and other AWS services to use machine learning for gaining insights from your satellite imagery. After ground station has ingested the data into a S3 bucket, as a first step, you might have some requirements for pre-processing ingested images. Sagemaker provides managed Jupyter notebooks, which you could use for your data preparation. Additionally, Sagemaker provides a capability called Sagemaker Processing, which helps you run your pre-processing tasks in a scalable way and decoupled from your development notebooks. This helps you optimizing costs as you pay only for higher configuration systems for running pre-processing tasks. The notebook further invokes Sagemaker's data labeling service called Ground Truth through APIs to label your datasets. The labeled datasets are stored back in S3 buckets. Once you have labeled dataset, you can use Sagemaker's training instances through simple APIs to train your models on very high-end GPUs and CPUs while still using very small configuration Jupyter notebooks for code development. After the model is trained, it can be deployed on AWS using Sagemaker's one-click deployment capability through Sagemaker endpoints. Sagemaker endpoints are just like REST APIs hosted in the cloud, which could be called by your applications. You can also create a pipeline to retrain your models that use new images from S3 bucket to continuously improve the training data and iterate on the models. For inferencing, when you receive images in S3 bucket, you can trigger an event to invoke a Lambda function, which is AWS's code as service capability, which in turn can call the Sagemaker endpoints to do a real-time or batch inferences on satellite images and store the results in a NoSQL database like DynamoDB. We also have Amplify, which helps you connect your front-end applications to your back-end with just a few lines of code, and then deploy them at scale. Not to miss the Amazon Simple Notification service used for notifications. I'm excited to know what problems of Earth would you like to solve using satellite data and Amazon Sagemaker. Jasminder, now that we have informed our audience about how to leverage machine learning on AWS, what are the other considerations that Earth observation customers should keep in mind?
Thank you, Seema. Earth observation customers must ask themselves, what is the temporal resolution that they require? What is the satellite revisit periods that will satisfy their use cases? Are these to fight bushfires or water management for agricultural purposes? What is the maximum latency that they can afford? In the bushfire example, the whole process needs very low latency because you need to notify authorities in a matter of minutes. On the other hand, for our agricultural use case, you probably don't need low latency. At the core of your solution, you must consider how often do your customers want insights from satellite data. At AWS, we understand that infrastructure should not constrain you from solving complex problems. Customers should be able to focus less on building and managing data centers, but instead focus more on the business outcomes and research initiatives. A great example of this comes from Satshore, which is a large area analytics company based in India. They use satellite data with machine learning to provide real-time insights for problems across multiple domains, like agriculture, environment, and infrastructure. Within agricultural monitoring, a single satellite can observe a vast area covering 200 by 200 kilometers. Their workloads grew at a scale of observing 12 districts in 2017 to 72 districts in 2018, and in 2019 to 150 districts. They've been able to scale without having to worry about the infrastructure by using AWS services. Satshore has built a data pipeline on AWS, which they use to pre-process satellite imagery and provide analytics to its customers. They ingest satellite data from sources like Earth on AWS into Amazon S3 buckets, from where an automatic workflow triggers Amazon EC2 spot instances to derive insights for their customers. With their solution, they've been able to focus on their customer needs and requirements. Now, what do we see in the future of Earth observation? Firstly, we will continue to gather more and more data from space-based sensors, which means data and analytics will play a greater role, with satellites producing large amounts of data. Processing this data to make it insightful for users and at greater speeds will become important. Secondly, space-based solutions will continue to make a wider impact into industries like shipping, agriculture, mining, resources, and climate change. And lastly, new startups will continue to bring innovative ideas and services to market using satellites and machine learning on edge. I'll leave you with a personal call to action. There are many public broadcast satellites like Aqua, SNPP, JPSS-1, and Terra. Use these to try AWS services like Ground Station. It is a fascinating experience to prepare your first set of satellite imagery and imagine yourself taking that picture. If you're interested in machine learning for your next space project, try our machine learning services like Amazon Sagemaker. And never, never be constrained by your computing power. With AWS Compute Services, you have virtually unlimited capacity. And lastly, please try AWS storage services like S3 to store and protect any amount of data for a range of use cases. It could be data lakes, websites, mobile applications, backup or restore, archive, enterprise applications, IoT devices, and big data analytics. We encourage you to engage with our training and certification content today. Skill Builder is our online learning center that makes it easier for anyone, from beginners to experienced professionals, to build AWS cloud skills. We offer 500 plus free digital courses that can help you and your team build new cloud skills, and learn about the latest services when and where it's convenient, in up to 16 languages. Within Skill Builder, take advantage of the flexible learning plans, which offer suggested digital courses aligned to a specific domain or job role. As you build your skills, consider preparing for one of our 11 AWS certifications. These industry-recognized certifications span foundational, professional, and specialty levels to validate AWS knowledge and skills, building your credibility and confidence. We invite you to join the AWS Certified community, which brings together AWS certified practitioners and builders in an exclusive online community. You'll participate in discussion forums, learning and networking opportunities, and challenges from the AWS team to earn rewards and recognition. Scan one or both of the QR codes on the screen to get started with your cloud skills training and certification. With that, I'd like to thank you again for attending, and we really appreciate your feedback so that we can better understand the topics and services you would like to know more about. So please do take the time to fill out our survey and let us know what you think. Thank you.